This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. So in the last lecture, we discussed the turbojet cycle, and we introduced the basic components in the system, and as well as the TS diagram. So, as said, the turbojet cycle is very similar to a Brayton cycle. It's all running. It's all one type of gas turbine cycles. Here, there is two differences that you want to notice. One is we have two new components, the diffuser and the nozzle, and there we need to pay attention to the change in the kinetic energy across these two components. And also, for the pure turbojet cycle, we have the turbine work equals to the compressor work, right? So the compressor work equals to the turbine work. That refers to the T4 minus T5 equals to T3 minus T2. So when the question asks you to draw a TS diagram for a turbojet cycle, pure turbojet cycle, you don't want to draw these two temperature difference being too different, right? So there should be more or less the same, or in calculation it should be exactly the same. But when you draw it, they should look more or less the same, right? So that's one, and the other one, as we said, the change in kinetic energy is not equals to 0 at the nozzle and diffuser. Diffuser, although it's a equivalent component working in the opposite principle as a nozzle, but diffuser is not always used. Nozzle certainly is always used for any aircraft propulsion using the gas turbines. But in principle, they're working on the same principle, but in the reverse way. And but other than that, for the rest of the system, if I use a dashed line box to indicate it, so for the rest of the system, the delta KE is equals to 0. So you may wonder, the gas is flowing. It certainly has the kinetic energy, right? And if the gas is passing through a compressor or turbine, its velocity certainly will change. Why we don't consider the kinetic energy change there? But in fact, the if you do a quick estimate, for example, if you have 1 kilograms of air, okay, so if you change the velocity from 0 to 30 meters per second, 30 meters per second, that's a pretty fast speed for our daily life. If you convert to the kilometer per hour, so it's about 108 kilometer per hour. So that's the fast you can drive legally on the highway, right? So if you consider that, you can estimate how much kinetic energy does in terms of the enthalpy. So there you can find that the kinetic energy, the mass-specific kinetic energy, that will be V squared, or I say delta KE, from 0 to 30 meters per second, divided by 2. That will be 900 divided by 2, so 450 joule per kilogram. Yeah. So if you consider how much this energy can, if I convert this much kinetic energy to the enthalpy, then the enthalpy would be delta H will equals to m dot Cp delta T. And I'm dealing with a mass-specific value, so this m dot basically is 1. So if you do that, you will find that delta T is equals to 450 divided by the Cp, right? For air, the Cp is typically around 1,000 joule per kilogram, right, per K. So then you will find that 1 Q will increase the temperature by about half degrees Celsius. So even you, the air is accelerated from 0 to over 100 kilometers per hour speed, you can only raise the temperature by half degree. So that's basically nothing compared to the temperature change going through the thermodynamic cycles there. Right? So that's something to be aware. But because this term is scaling with V square, if you have 10 times of the velocity increase, for example, for the 300 meters per second, then you will have this one to be 100 times larger. So it's 50 degrees Celsius difference. So at that condition, you want to consider that factor in terms of the kinetic energy change caused the temperature change there. All right, so that's something we want to be clear with. And we mentioned that the energy balance across the nozzle or diffuser can be written as, for example, okay, so if I mark 1, 2, 3, 4, 5, and 6, right? So that's indicated here. So across the nozzle, we have the enthalpy 5 plus the kinetic energy of 5 equals to H6 plus the kinetic energy of V6. As we said, this term is going to 0, essentially. Not absolute 0, but it's negligible compared to the rest terms. Then we have the H5 equals to H6 and the kinetic energy term at the nozzle exit. All right. So there is new term we can define, which is essentially combine the enthalpy and the kinetic energy term. That's called stagnation enthalpy. right? So stagnation enthalpy is a new term, but essentially there's nothing new except that it's a static enthalpy. So this one called the static enthalpy plus the kinetic energy. So basically, it's a two terms combined together. Now we call it as a stagnation enthalpy. So stagnation enthalpy actually is quite useful, particularly when you're dealing with high-speed aviation, and if you're dealing with compressible flow, and often that's the concept being used. So let's say a few words on the stagnation property. Stagnation property is essentially, by definition, it says that it's a property attained when something is moving at a certain speed and you force it to stop. And this process is isentropic. So the enthalpy or the property you obtained at the end of this process will be the stagnation property for this process. All right, so that's property attained by a moving object brought to a stop isentropically. So if we write the first law for this process, so that will be Q minus W equals to enthalpy change and equals to the kinetic energy change. Again, so when we're dealing with stagnation property, the speed or the associated kinetic energy is not something you can ignore. You always consider the kinetic energy. So there, this process, as I said, is isentropic. So this Q goes to 0, and this process does not do any work. No outside work being done to the system and no output work from the system. So both of this goes to 0. So then if we call the initial state is 1, we are equals to, so this one goes to 0. And then equals to H2 plus HV2 squared. And we said that it's brought, the object is being brought to a stop, right? So this V2 is equals to 0. So this one is gone. Then this saying that this H2 is equals to the static property of state 1 and the kinetic property of the state 1. So here we can say the HT1 equals to HT2. So this is basically saying that from the process, if you define the stagnation enthalpy of the state 1 as a combination of enthalpy, static enthalpy and the kinetic energy, you will have HT1. And HT2 will just equals to its static enthalpy because it doesn't have any kinetic energy attached to it. Right? So again, stagnation property is just a combination of static property plus the kinetic energy. So there is a set of properties can be defined following the definition there. So if you want to determine, so if we say HT is, the T actually stands for total, but we often use the T for the for the stagnation property. Ht equals to h plus the v squared divided by 2, right? So from there, we can determine what's the stagnation temperature. So this is stagnation enthalpy. So if we have a Cp T stagnation temperature, that can be written as Cp static temperature and V square T. Right, so then we can find how to determine the stagnation temperature. So that's static temperature plus V square 2Cp. Directly related to the enthalpy relation. And if you're dealing with ideal gases, if you have ideal gases from the start state to the end state, this process is isentropic, right? Then you can apply the isentropic law to this process to figure out the stagnation pressure. So that's based on the similar idea. So for ideal gases, then you can find the pressure, stagnation pressure, over the static pressure equals to the stagnation temperature, static temperature to a relation of this. So sometime that you are asking to calculate this properties, but they are all coming from the relations that we have known. That's just a new term, but essentially that's not new. It's just a combination of two terms: static enthalpy, static property, and the kinetic and kinetic energy related property. So nothing really new there. All right, so that's the theoretical part for this turbojet cycle. So turbojet is, as we said, is more like a theoretical cycle. But indeed, when people first apply the gas turbine to aviation, the first aircraft is indeed running on the turbojet cycle. It's not. It's different from the aircraft engines being used today. So I show you a picture of this. Right. So this is a picture of the first turbojet that's being built, and that's in August 1939, when this aircraft running on the turbojet cycle, turbojet principle being first flown. And if you know some important date in history, this date actually is very close to one of the important event in the 1930s, 1940s. Anyone know that? So if you should have taken some of the history subjects in high school, right? At least in high school. The Second World War starts on the 1st September of 1939. So just a few days after this, right? But when this aircraft is first flown, is far away from the military use. So when this actually being demonstrated to the German Air Force, that's actually a few months after this, and in fact that demonstration is not very impressive to those military officials. So this gas turbine powered engine has not actually been developed for the military use after the Second World War. All right, but in any case, this is an important event in terms of the aviation. So this is the first time that you have the jet aircraft. So previously you only have the piston powered engine. And once this technology gets matured, and then quickly kicks the piston engine out of the aircraft aviation. All right, so that's the one. But the turbojet engine is not very used much today. And the reason for that is it has certain strengths, but it has also very significant shortcomings. The strength is it has high velocity. If you design the system right, it can produce very high velocity jet, so that it can propel the aircraft running at high speed if you do it properly. The one we just shown, actually, when it's being demonstrated, is only flying at like 0.5 Mach number, 0.5 of the speed of sound. So that's not very impressive for the very first design. But the major problem is it's has a low thrust. So in terms of the propulsion force it can produce, it's not very much. And the other one is low efficiency. All right. The thrust we mentioned, the thrust is a force applied to the aircraft to push the aircraft to go forward, right? So that one can be written as the amount of air that is going through the engine, where the velocity at the exit minus velocity at the inlet. The inlet velocity, basically, that's the velocity of the aircraft, right? Because that's just you assume the air is static there, and then the relative velocity is the aircraft is one for the aircraft. So that's the it cannot produce very much thrust, although the exit velocity can be very high, and it can push the aircraft to fly at a relatively high speed. But the thrust is relatively small. And the efficiency actually is a two component. So one component, if we call it overall efficiency, one part is the thermal efficiency, which is related to how the energy being converted from the chemical to the kinetic. And the other one is called the propulsion efficiency. Propulsion efficiency is saying that you have this much kinetic energy is converted, how efficient that kinetic energy can push the aircraft to, is being used to push the aircraft to move. All right? So these two can be individually defined. So this one can be written as it's a typical definition, the useful output versus the required input. The required input here is the combustion heat input in the combustor, and the useful output is the kinetic energy that you can create, right? The kinetic energy you can create can be written as the m dot air and the v exit square minus v inlet square divided by 2. So that's a useful output versus the required input. So that's a thermal, that's a typical, that's a similar definition as we use to determine the Brayton cycle. And the propulsion is a bit of different. So the propulsion is defined by the out of this kinetic energy, how much is being used to push the aircraft going forward. So that's being calculated as the momentum of the thrust times the velocity that the aircraft is flowing. So if I say that's inlet, divided by the kinetic energy that you created here. So that's delta KE. And I want to. Oh, okay. So if you quickly rearrange, bring this equation to here, bring this equation to here, and bring this to there, you can find this propulsion efficiency can be written as 1 plus the velocity of the exit over the velocity of the inlet. So that's how you calculate the propulsion efficiency. So there you can see that if you have a larger exit velocity, this term will become larger. The denominator will become larger. Actually, it will bring down the propulsion efficiency. Right? So if you understand that kinetic energy, if leaving the aircraft being too high, then you would have the kinetic energy which is stored in the jet leaving the aircraft. So that part of kinetic energy is not being used, but just being dumped to the ambient. So a similar concept compared to if we're running as a heat engine, if the Q out, if the heat that we dump to the low temperature reservoir being too high, then that cycle wouldn't be efficient because that part of heat is not being used to work. It's just throwing it away. So a similar idea here. If the jet leaving the aircraft at a much higher velocity compared to the aircraft flying speed, then you got more loss in terms of the kinetic energy that you created in the engine. Right? So that one saying that if the exit velocity going up, the propulsion efficiency will go down. So this actually giving us some rule of thumb in terms of the how to produce large thrust or how to produce more efficient jets. So there's a 2 rule of thumb. So one saying that if you want to produce large thrust, you do not want to produce high velocity jet. Instead, you want to produce a large amount of air, flowing air, and moving at a relatively slow speed compared to a small amount of air moving at a very fast speed. So the former case will give you a large push in terms of the aircraft. All right? So that one saying that a larger amount of air moving at slow speed produces higher thrust than a small amount of air moving at high speed. I should say low speed instead of the slow speed. Low speed there. So that's the first rule of thumb. So do not produce a high velocity jet like the turbojet case. You want to do something else to try to move a larger amount of air. And that air can moving slower, but it can give you a larger thrust. All right, so that's one regarding thrust. And the rule of thumb for the efficiency saying that the high efficiency occurs when when the aircraft design speed matches the engine exit speed. So if the engine is if the aircraft is a subsonic aircraft, you do not want to having install engine which is running at a supersonic manner. So because in that case you will lose a lot of kinetic energy that you created, right? So if you're looking at the equation here, if you have the exit velocity match the inlet, as said, the inlet basically is the aircraft flying speed, then you will have a 1 there, right? So that will give you the maximum propulsion efficiency of 1, because this exit velocity must be higher than the inlet velocity in any case. All right. So based on these two rule of thumb, the pure turbojet cycle has been modified, and that's is more close to what we see today. So we are going to discuss the modification of the turbojet cycle. So there is a there is a few things that has been done. So this is a pure turbojet. We have the compressor, turbine, and the nozzle, right? And a more common type of engine used today is called turbofan rather than turbojet. So what turbofan is, you have a fan, which is in front of the compressor, and then you have a maybe I should say here. You have a fan there, which is to drive amount of air, like incoming air, and only part of the air going into the combustor, and the rest of air actually just passing through the engine. I should say not passing through the combustor, only a fraction of air passing through the combustor. Then they join at the end and produce the thrust. The idea is you have larger amount of air in that being created in that case to give you a larger push of the aircraft. And another one is called the turboprop. Turboprop is similar to the turbofan, except you do not have the fan there. Rather, you're using the turbine to drive a propeller at the front of the engine. And also you have the turboshaft, which is similar to the Brayton cycle, where the output is no longer thrust, but just the shaft work. All right, so we'll see some examples there. Okay, again, this is a more detailed structure of the turbofan. So where you have the fan there, right? So actually, this is a better illustration. You have a fan there to bring the air in continuously, and you have the compressor, which is here. So part of the air actually is going in the duct in this purple area, not going through the engine. The rest air going through the combustor, going through the compressor, then combustor, then going through the nozzle. All right, and they joined at the exit of the nozzle. So you have some amount of air which is just passing through the fan, not going through the combustion process. So they have a relatively low speed, but at the end, when they join this high-speed jet, they will mix together and form a jet, which is the velocity in between of these two streams. Then it has you have a large amount of air giving you moving at a relatively slow speed to give you a higher thrust. Right. So that's the concept there. So the turbofan is a fraction of air passing through the fan. The fan actually is acting as a low pressure compressor. Which bypass the combustor and join the high velocity jet at the exit of nozzle. So you understand the idea is to produce, to move a large amount of air. Although the speed is not as high, but you can have higher thrust based on the rule of thumb there. So here we have a parameter called the bypass ratio. So this one basically is saying that there is how much air that is not going in the engine and how much air going in the engine, right? So this one is amount of air which is in the duct versus amount of air in the combustor. So that's a parameter that you can adjust or you can design when you design the aircraft. And depending on the application, you can use different bypass ratio for different applications. So any idea in terms of if I want to have a low bypass ratio, what would be the application? A low bypass ratio means you have a minimum amount of air in the duct and most of air which is in the still going through the combustion, right? So that's more like a turbojet case. If you have a turbojet, what should be the bypass ratio? Yeah, it should be 0, right? So if you have a small bypass ratio, which is saying that this engine is still more or less like a turbojet, which means it still can fly at high speed, and which application require high-speed flight? Fighter jet. Yep. So let's see. I think I have an example here. So this is a F-22. So it's probably still one of the most advanced military aircraft or fighter jet today. So this one has a bypass ratio of 0.3, so which means only 30% of air compared to going through the duct compared to the air getting in the engine. So this craft can fly at a very high speed. Actually, one of the features is called a super cruise. So this aircraft can cruise at a supersonic speed, which is a quoted number is a Mach of 1.8. So 1.8 times of speed sound during cruise. Cruise means, in that case, the engine is running at the most efficient mode, which means the engine only produce enough power to overcome the drag on the aircraft. So there is no acceleration. But in that case, this aircraft can still running at the supersonic speed. Yeah, so that's one of the low bypass. You will have high speed, flying at a Mach number of 1.8. So if you increase the bypass ratio, which means the speed will become slower, but you can produce more thrust. All right. So what type of application is there? Commercial flight. Yep. So that's the one I'm showing there. So this is Airbus 380. And this engine has a bypass ratio about between 8 and 9. So which means there is 8 to 9 times of air not being burned, just passing through the engine cover, which we call the nacelle, just passing it without being burned. And then only 1 out of 9 parts of air going through the combustor, going through the nozzle, and then mixed with the rest 8 to 9 parts of the air. Then it can produce a large thrust. All right? So it can produce high thrust, and it's also high efficiency. Oh, sure. And for the commercial air flight, the fuel cost is the one of the most controllable cost. And if you pay attention to the air ticket price, usually if the fuel price goes up, the air ticket price will definitely goes up, right? So the fuel cost accounts for like a quarter of the total operation cost of the airline. So if there is a new type of engine which is more fuel efficient, definitely the airline company they want to buy those engines. They want to buy those aircrafts. So this for the example of this would be A380. Right. So it has a bypass ratio around 9, and its highest flying speed is around 0.8 Mach number. All right, so this is for the commercial flight, and this is if you probably everyone should have heard the news that recently we have these Boeing 373, this model Max 8 that crashed in Africa, and this is the second time that this model crashed. So there is a particular reason to cause that crash. But just in terms of the aircraft, this is really a new model. Actually, it's just come on being produced like 2 or 3 years ago. Start to come online, and this is certainly one of the latest model for the 737. 737 started. I do not remember exactly, somewhere around 1990s. So it's already started earlier, but over the years has been improved gradually. So this new model, actually, in terms of the performance, they are pretty good. So you can see that compared to the previous model, it increased the bypass ratio from 5 to 9, and that gives the fuel saving, the fuel economy, or fuel should be fuel economy, about 10 to 12%. So that's pretty large saving, and that's airline is really care about. And also it can produce a larger thrust due to this larger bypass ratio. I look at the number, is about during takeoff it can produce about 20 to 25% more thrust. Right. So in terms of design, that's pretty good. It's also using the carbon fiber in the fan, and actually the aircraft is running a lot quieter compared to before. But certainly there is something wrong there, right? And I think the official report will be released. But based on the last accident, which is a couple months ago in Indonesia, people find that this aircraft, potential reason is you have a large engine, you have more thrust to push the aircraft during the takeoff. So there is a tendency that the aircraft tend to go. So if you consider the angle of attack, so which means when the aircraft is taking off, the nose is going up, right? So it has a tendency that the nose being pitched too high. So in that case, during the test flight, the company noticed a problem. So they implement software to automatically crack that trend. So when the aircraft during the takeoff, if it detect, not really during the takeoff, during the flight, if they detect that the nose being too high, then that automatic software, or that software automatically kick in, try to tilt the nose down. So that happens without, that's coming automatically without the intervening of the pilot. So, but the problem is if you have whether the software detects the nose being tipped too high or not, depending on the measurement on the aircraft, right? Depending on certain sensors on the craft. If those sensors give you the faulty signal or faulty measurement, then that causes the software to come in, then it can become a problem. Because the aircraft actually is not tilting down, but the software try to keep the aircraft going down, right? So people suspect the reason is because of faulty measurement on the aircraft. This software come in by itself and try to take control and try to ask the aircraft to tilt down. But the pilot certainly noticed that's not the case, and they try to bring the nose back. So this back and forcing eventually leading to the aircraft to crash. So the company actually said that this automatic kicking can be disengaged, but that requires the pilot to be properly trained to know that and disengage it at that moment, then take the manual control. But certainly that didn't happen, and that's very unfortunate for that particular case. But back to our discussion here. So this aircraft is one of the latest model, and that actually try to be designed to be more efficient and give you more power, more thrust at least. All right, so that's the turbofan. And another version or another development above the turbofan is people saying that people are thinking that if I want to produce even higher thrust or have a even more efficient design, why I still need the fan, right? A fan with the engine cover still limited the amount of air or amount of bypass ratio that I can have. Why not I just get rid of the engine cover, just using a propeller in front of the engine, so that I'm just propelling open air. The bypass ratio can be infinity, right? So that's the other design called turboprop. So the idea is that turboprop is remove the engine cover. and allow even larger bypass ratio. So in this case, you're really after the thrust for certain applications. And an example of this, actually, this is just a demonstration of the turbofan. You have the fan, which you get rid of the engine cover. So the fan is running, and you could still have certain amount of air going inside, get burned to drive the turbine. And then you have a very large bypass ratio for the process. All right. So example of this is the military transport aircraft. So in this case, it's really heavy duty, and you want to have large thrust to drive this big aircraft. And in this case, they don't need to fly at a very high speed because the purpose is for transporting. It's not for the fighting. Right. So in this case, the example would be the 3130 Hercules. So that's transport aircraft. And this one flying at a speed is around half speed of sound. So you can have a large thrust to get this aircraft to going, but doesn't need to be running at a very high speed. All right, so that's basically it's the variation of the turbojet, which is more practical in terms of real application. Okay, I think that's probably it today, and I'm going to try the TS diagram in tomorrow's lecture.
Just quickly for the propulsion efficiency, I thought I heard you say momentum, but I thought you wrote an F, so I wasn't sure if that's supposed to be force and momentum in that equation.
Oh, it's the momentum times the...
Times the inlet velocity.
Yeah.
Okay, perfect.
Yeah,
That's
yeah.
what I thought. I just wasn't understanding.
There you go.
I'm quite confused about efficiency because like thermal efficiency is just so I can rewrite it's like this way
The one
and and so for the thermal efficiency, it's just like
the upper power.
like this, and for the proposal, and I can cancel these two. So
When like
right, so it's just like velocity as axis is not. If I increase the velocity as axis, the total overall efficiency would increase.
Wait, so as the velocity increases.
Because I cancel
Efficiency of propulsion.
I cancel
Yeah,
the
but because the
exit
whole
velocity
efficiency is
did
the
not
multiply
Yeah.
of these two.
So basically, it's just saying if that
Are you
increases,
saying the
then that decreases.
are you talking about the total or just the
total efficiency.
Yeah, the total efficiency.
It's just
Multiply by thermal and
Yeah.
Yeah.
population.
and after I
But
can
like in the
He's trying